Alright, so you are welcome to the GMAETS 41's live stream section. So in this particular video, we are going to give attention to past question review, okay? Seemingly exam focus review on Chem 101, basic inorganic. Place, I'd like to say that this is also based on test work that was done, from the GMAETS 41's online class. Like I mentioned in my last live stream session, although the school is on break, we respect that, putting our physical class on hold for the break as well too, pending when school resumes, because that should be next week, when the physical class will also kick off. However, the GMAETS 41 always carries out his online classes. And so whether break is on or not, we keep learning. So I'd like us to give answers to 15 questions that have been drafted out. These are, likely exam questions. And these questions are based on two topics in Chem 101. That is quantum numbers and principles of filling atomic orbitals. So you can see I decided to share our learning class, okay, with your friends, so you can see the questions as I give answers to them. Meanwhile, this our learning WhatsApp community or group, our video lessons and lesson notes are embedded in the GMAETS 41's Telegram channel. So if you register with GMAETS 41's tutorials, you get access to the Telegram channel, so you can also follow up with the online classes. So the video lessons on this have been taken by the students, and we have these quiz questions, okay, that we put forward and we want to give answers to them. So the first question here, which of the quantum numbers determines the energy sublevel in an orbital? And of course, the correct answer is azimuthal quantum number. Azimuthal quantum number. Actually, azimuthal quantum number, gives us information about the subshell. Subshell, that is the meaning of that sublevel that you have there, in which an electron belongs to. Is that okay? So the subshell in which an electron belongs to. Azimuthal quantum number gives us information about it. So the correct answer is option C. And of course, I've clicked on that. Now we are moving on to question number 2. And now question number 2, we have how many unpaired electrons are in the p orbitals of a fluorine atom? How many unpaired orbitals are in the fluorine, in the p orbitals of a fluorine atom? And how do we answer this question? We just have to have in mind, the electronic configuration of fluorine. And of course, we can use our normal O-level electronic configuration, where you draw atomic structures using circles if you wish. The first approach to this, you can use your SPDF approach. So if you write the electronic configuration of fluorine is atomic number 9. You should be getting something like 1s2, 2s2, and 2p5. I will display that on the screen for you to take a look. All right. So let's see. I just said something about the electronic configuration of fluorine. This note is an extract from the GMAETS 41's Telegram, okay? On quantum numbers. So if you want to learn more, get registered, join the GMAETS 41's tutorial, and you get access to all these learning materials. Like I said, the GMAETS 41's video lesson covering all the topics in the courses that we take you. From our playlist, you can see these courses, Math 101, Chem 101, Physics 101, Chem 107 Practical, Physics 107 Practical, and many more. So you can see that question number 2, fluorine. Okay, we have the electronic configuration 1s2, 2s2, and then 2p5. If you have challenge on this concept of electronic configuration using the orbital form, the subshell notation, you can always go to GMAETS, and of course, the platform will help you. So you see, how would we now get the unpaired electron? What we have to do is to reach out for the orbital that shows the last electron. And the orbital you can see is that of 2p. So you have 2p5. Normally the p orbital is meant to carry, 2 electron. P has I think 3 degenerate orbital, that is px, py, and pz. Each of them gets 2. So if you add it up, 2 in the px, 2 in the py, 2 in the pz, you are going to get that p orbital is meant to contain a maximum of 6 electrons. But if you look at this 2p, we have 5 electrons. So to know the unpaired electron, you're going to do the maximum number of electrons that p is supposed to contain, which is 6, and then minus the 5 electrons you're seeing there. 6 minus 1, 6 minus 5 rather, is going to give you 1. Yeah, 6 minus 5 is going to give you 1. It means that fluorine has 1 unpaired electron. Fluorine has what? 1 unpaired electron. And of course, the correct answer there is option A. So I'm clicking that for you to see. Alright. So this takes us to question number 3. What is the valence shell electron configuration of the element with atomic number 17? This question, interesting. Sadly, all entry, were incorrect. Yeah, the entry provided, you can see option A being selected, but that's not the correct answer. Okay, that's not the correct answer. That option A is the electronic configuration of chlorine with atomic number 17. But hey, take a look at the question. The examiner is requesting for the valence shell electron configuration. I repeat that. The valence shell electron configuration of the element with atomic number 17. So when you hear valence shell, it simply means the outermost shell. We can also use the name ultimate shell. So if you're asked the configuration, of the valence shell electron configuration, we are simply interested in the number of electrons in the valence shell, in the outermost shell, in the ultimate shell. I hope I'm communicating. So from the electronic configuration of atomic number 17, which of course goes with chlorine, all you have to do is to check for the highest principal quantum number. Now for the A that the majority went for, if you look at the highest principal quantum number, there is 3. So you have 3s2 and 3p5. These two guys, 3s and 3p, they belong to the same energy level. Principal quantum number 3. Yeah, or radial quantum number. Take note. Principal quantum number is also called radial quantum number. Alright, so we have 3s and 3p. So that is the valence shell. That is the valence shell. So in answering this question, the valence shell electron configuration of an element with atomic number 17 is going to be 3s2 and 3p5. And so the correct option is option C, 3s2 and 3p5. So I'm going to click on that option C. That's the correct answer. You can see an analysis to this guy. So we've got this. So now question number 3, chlorine. The normal electronic configuration, using the subshell format is 1s2, 2s2, 2p6, 3s2, and then 3p5. So you can see that I underlined 3s2 and 3p5. And I call that the valence shell electrons. So that valence shell electrons, all you just have to do is to check you have 2 and 5 there. So the 3s2 and 3p5 is the outermost shell. Okay, so that's the electron configuration as the examiner requested. So the correct answer once again is option C, selected. Now let us move on to question number 4. One of these is not a principle of filling atomic orbital. So when filling atomic orbital, generally we have 3 main principles that guide us. We have the of-Bohr's principle, the Pauli's exclusion principle, we have the Hund's rule of maximum multiplicity. So the first 3 options are principles of filling atomic orbital. So the one that is not among them is the Bohr's rule of maximum electron. That is not a principle of filling atomic orbital. So the correct option is D, and all entry there correct. If you wish to learn more about this, remember the GMAETS 41 is here for you. You can always contact GMAETS 41 to join our tutorials, whether physical tutorial which takes place in UNIZE campus, or if you wish to join the online class, you're always welcome. You can become a channel member. Alright? To become a channel member, just simply click on the join tab below this video, then select, I always advise select the platinum level or the diamond level above, okay? Yeah. Select the platinum level, the diamond level. That will give you access to our video lessons, our learning materials, okay? Then to join our physical tutorial, you can contact GMAETS 41 for further information. Alright, which of the following orbital does not exhibit degeneracy? That's question number 5. So, a student will have to understand what degenerate orbital really is all about, or what degeneracy is all about. Okay? So, the correct option there is option B. S orbital does not exhibit degeneracy. Take note. S orbital does not exhibit degeneracy. When you talk about degeneracy, actually is the idea of, orbitals belonging to the same energy level. So S orbital does not exhibit. It doesn't possess degeneracy. So there's nothing like degenerate orbital in S orbital. So the correct option is B. And this takes us to question number 6. Mind you, if you have any question, feel free. You can drop your question, alright, in the comment box. And possibly, I will attend to the question at the end of this live session. Question number 6. The maximum number of electrons in an atom with principal quantum number n equal to 4 is... So it's also a simple one. We are being asked the maximum number of electrons that can be contained in an atom with principal quantum number n equal to 4. So what we do is to use the Bohr-Berry scheme. The Bohr-Berry scheme, there is a formula for determining the maximum number of electrons that a given principal quantum number can contain. And that formula is 2n raised to the power of 2. 2n to the power of 2. So that n is squared. Now n value was given here, and the n value you can see is 4. So all you have to do is 4 square, and then 4 square is going to give you 16. Multiply that 16 by 2, and then you're going to get 32. So the correct answer is 32. Let me turn off this fan. Alright, so I'm hearing something like, ooh, okay, let it not disturb you guys. Alright, so the correct answer is 32, like I said. All you have to do is square that 4, which is n squared, you get 16, then multiply by 2. The correct answer is D. I hope you are learning, you're following up, even though maybe if you are not part of us yet, at least I've been able to display in our WhatsApp group where we undertake closed learning for registered member. You can see the questions, okay? These are likely exam-focused questions, and of course, some of them are past questions extracted from this topic that we are considering, quantum numbers and principles of filling atomic orbital. All right, question number 7. Question number 7. The total number of orbital angular momentum quantum number is equal to... The total number of orbital angular momentum quantum number is equal to... The first thing a student will have to do here is get to even know which quantum number is called the orbital angular momentum quantum number. And I'm going to tell you that our quantum number is also called the subsidiary quantum number. The only thing is that most times students they get used to the one called the azimuthal quantum number. Yeah, most times students get used to that one, azimuthal. Please take note. Azimuthal quantum number is the same as subsidiary quantum number, and it is also the same as the orbital angular momentum quantum number. So the examiner asked, the total number of orbital angular momentum quantum number is equal to what? And so the correct answer is option C. You see, the total number of azimuthal quantum number is equal to the principal quantum number. I'm going to click on that. Option C, that's the correct answer. So, sadly, no option, really, no correct option came in for that. Okay, so, an access to the GMAETS 41's video lesson or lesson note on this will explain why the correct answer is C. On this channel, if you go through the GMAETS 41's playlist, you would see Chem 101 playlist for channel members. You can take that and then you see the answer to this question. Also, on our Telegram channel, you have the video lesson that explains the concept of quantum number and principles of filling atomic orbital. But I'd like to show you something. Why is it that the correct answer is option C? Why? Let me take you to the analysis, and then I'm going to show you from the lesson notes. Now we have this, question number 7. Yeah. Now I had to come up with an example. Let us assume that we are treating the principal quantum number n equal to 3. Principal quantum number n equal to 3. Now I want to get the orbital angular momentum quantum number, the total value. And that orbital angular momentum quantum number, also called the azimuthal quantum number simply, we use L to represent it. So that is the L that you are seeing there. We use L to represent it. So if n is equal to 3, the principal quantum number, the azimuthal quantum number, the orbital angular momentum quantum number, the subsidiary quantum number is going to be equal to 2. Why? Because L is equal to n minus 1. And so if n is equal to 3, then L is equal to 3 minus 1, which is going to give you L equal to 2, the azimuthal quantum number. But pause for a moment, please. The azimuthal quantum number, also known as the orbital angular momentum quantum number, which gave us L equal to 2 here when the principal quantum number is 3. What is the total number of orbital angular momentum quantum number for this L equal to 2? Now you can see it in brackets. The value of azimuthal quantum number usually starts from 0. So if L is equal to 2, is it that value that we obtain from the formula? L, permit me please to be a bit layman, okay? Let me pronounce that L. L, okay? L. If L is equal to 2, that formula that L is equal to N, don't mind me. L is pronounced L. But just for clarity then, for some people to follow up what I'm pronouncing, then N is N, okay? Now we have this relationship that the azimuthal quantum number L is equal to N minus 1. Now if N is equal to 3, and you do 3 minus 1, you get 2. Please take note of this, please. That answer you got is the final value of the azimuthal quantum number. So in this case, L equal to 2 is the final value. Now to get the total azimuthal quantum number, the total orbital angular momentum quantum number, the total subsidiary quantum number, you have to start from 0. And then you move down to 2. So that's going to be 0, 1, and 2. So how many orbitals do we have there? Yeah, how many subshells in that case? We have 3. Are you following, right? 3 of them. And that 3 subshell, you can see I drew an arrow to show total L, total orbital angular momentum quantum number is equal to 3. And that agrees with principal quantum number, which is 3. So when principal quantum number is 3, you expect that the total orbital angular momentum quantum number will also be 3. So if I ask you, suppose the principal quantum number is given as 5. What do you expect to be the total azimuthal quantum number? It's also going to be 5. but the last value will be 4 because they're going to do 5 minus 1. All right, so that is that. And of course, we have the lesson notes and of course the video lesson explaining that further. All right, so these are the concepts of the quantum number. This is a azimuthal quantum number. So you can take a look at that point where I wrote notes. The total number of L values is equal to n. And I explained something briefly about that. Okay, we are moving on. Let us go back to our next question. The next question is question number 8. I'm going to be a bit fast now, okay? Yeah, like I said, to learn more, the GMAETS 41 is always here. You can join us for detailed learning, okay? You can join us either physically or online. Online here, just become a channel member. And also contact GMAETS to actually apply for the online where you get access to our Telegram channel for all the video lessons and lesson notes. Then of course, you can join our physical tutorial, especially if you're in Unizik. All right, for Unizik students, the class takes place on campus there. Question number 8. Which of the following orbitals has a double dumbbell geometry? Which of the following orbitals has a double dumbbell geometry? The correct answer is option C. Yeah, option C. So the d orbital, the shape is double dumbbell. Take note of that. Now move on to question number 9. The maximum number of electrons that sp, d, and f orbitals can contain are respectively. Yeah, you can find out from a lesson note and video lesson. I explain how that total number of electrons that each of these orbitals can contain, how it's been obtained. But the correct answer is option D. We have 2, 6, 10, and 14 respectively. X carries a maximum of 2, P a maximum of 6, D a maximum of 10, and of course F a maximum of 14. So I'm going to click on that. All right, this takes us to question number 10. Yeah, this question is an interesting question. First of all, let me start by saying that I purposely decided not to drop the correct answer to this question number 10. So take note of that. The correct option is not there. And like I said, sometimes when I provide related exam questions like these, are you following, right? I try to increase students' confidence. And of course, I used to tell those on a learning platform, you want to be confident of what you know. All right? So for this particular question, the correct answer is not there. And I requested that students should be free to drop their suggested answer, which they feel is correct. Now let us make the analysis of this particular question. The last shell of a given element is 5f7. That is 5f, and then the number of electrons is 7. What are the values of n, l, m, and s? N is the principal quantum number, L the azimuthal quantum number, m the magnetic quantum number, and then s the spin quantum number. All right, so clearly you want to take note that the principal quantum number n, the first one, n, is equal to 5. That 5 that is attached to that f, that is the value of the principal quantum number. Are you getting right? Yeah. So n equal to 5 straight on. Then L, the azimuthal quantum number. Yeah, to obtain it, we are meant to do n minus 1. N minus 1, which of course will give us 5 minus 1, which is equal to 4. However, don't just quickly jump into concluding that that 4 is the value of L. Please take note of the subshell configuration whose orbital was used here. And that subshell configuration whose orbital was used in that 5f7 is simply F, the f orbital. So if L is equal to 4, you know the reason, 5 minus 1, you get 4. That 4 has values from 0 like I explained in previous question. So you have 0, 1, 2, 3, and 4. Once again, 0, 1, 2, 3, and what? 4. So you have to ask yourself, which particular number is associated, is designated to the f orbital? And I want to tell you that it is 3. Are you getting me right? 3 is associated. That is the designation of f orbital, which means out of that L value that is 0, 1, 2, 3, and 4, we are picking the value L equal to 3, which means for this guy, the value of L is 3. I'm going to show you the analysis, okay, so that you follow up on screen. And so we have this, okay, look at that, question 7, right? Oh no, we're in question number 10. So this is the analysis. N is equal to 5. I've explained that L would give you 4 because N minus 1 is equal to 4. But then you need to get the total number of L value, which will now start from 0 and end with 4. Right, so you have 5 orbitals there. But the particular value for L out of 0, 1, 2, 3, 4 is 3. And that is why you have L equal to 3 for f orbital. For f orbital. Okay, take a look at this GMAETS 41's tutorial notes. Then you get a clear picture of what I mean by that. This is the designation, azimuthal quantum number. You can see azimuthal quantum number, azimuthal QN. So you have 0, 1, 2, 3. Now this is the designation given to them. S orbital, that's what bears that 0. P orbital bears 1. D orbital is associated to 2. And then F orbital, we give it 3. The L value, the azimuthal quantum number for these guys, that's what is written there. So if F is designated with the value 3, it means that for all these values 0, 1, 2, 3, and 4, the value of L is going to be 3. Since the orbital given, you can see it is 5F. F. So that F is of importance. The azimuthal quantum number for F is 3. Good. And because we have been able to get the azimuthal quantum number to be 3, that now helps us to get the magnetic quantum number. And magnetic quantum number goes from minus L through 0 to plus L. So if our L value for this question is 3, then the magnetic quantum number value M is going to move from minus 3 through 0, then through to plus 3. If you want to expand that, you can do so. Minus 3, minus 2, minus 1, 0, 1, 2, and 3. So this magnetic quantum number in the options provided, are you following, right? None of them had that value of magnetic quantum number, minus 3 to 0 to plus 3. And that is why there is no correct option there, like I said. And I did it on purpose. Yeah. The GMAETS 41 trains you to become confident, understand what you're studying. All right, so that any day, anytime you sit for an exam or it becomes necessary for you to explain a concept, you'll be confident in what you're doing. Like in exam hall, you'll be sure that your examiners, they have nowhere to dribble you to. That is the idea. First class is the goal. The language that GMAETS 41 understands academically. All right, let us now look at the spin quantum number. How do we get the spin quantum number? All we have to do is to go back to the f orbital and ask ourselves. F orbital has 7 degenerate orbitals. Yeah. Now let me give you one hint a little bit. I guess we are going to meet a question related, I don't know, as we move on. S orbital does not have a degenerate orbital. We've talked about that. We met a question on it. P orbital has 3 degenerate orbitals. I've talked about that in one of the questions I analyzed. Then D orbital has 5 degenerate orbitals. While F orbital has 7 degenerate orbitals. So for us to get the direction of spin for this particular electron in 5F7, all we have to do is to quickly draw out the 7 degenerate orbital of F, because we are dealing with an F orbital problem. If it is D orbital problem, we are going to draw degenerate orbital with 5 columns. I think this one is 7. 1, 2, 3, 4, 5, 6, 7. Because F orbital has 7 degenerate orbitals. So what is now going to be the spin quantum number? Now we'll go back to the 5F7 given to us. That's 7 is the number of electrons, okay? Is the number of electrons. So come to this block and using Hund's rule of maximum multiplicity. I repeat, using the principle of filling atomic orbital which Hund's rule proposed. That's 7 electrons, we will distribute it into these blocks. Each block is meant to contain a maximum of 2. But according to Hunt's rule, you are expected to fill them singly first. And then if the number of electrons still continues, you come back and start pairing. And when you are filling, by convention, the first filling, we give it upward spin. And upward spin is positive. So that is why you have, in filling the 7 electrons into the 7 degenerate orbitals of F, the first block filled with an upward electrons, the second block, upward electron, third one, the same thing, fourth one. As you are filling with single electron, it will be up, up. Okay? But then, when we got to the last block, you notice that we have gotten the 7 electrons. No electron to distribute anymore because we have 7 electrons there, okay? Therefore, it means that the last electron, the direction of spin is upward, which is positive. That is why the correct answer for the spin quantum number for this guy is plus half. If maybe the spin is downward, it would have been minus half. And I'll give you an instance. Assuming that maybe the 5F7, let's assume it is 5F8. 5F8, so you have 8 electrons. When you get to the last block, that's block number 7, you've gotten 7 upward spin. Now you go back for the 8 electron, you come to the first block and start pairing according to Hunt's rule. And when you start pairing, the spinning will be downward, which means the 8 electron will enter downward, okay, anti-clockwise spin. But for this question, the 7th electron, was an upward spin. So the spin quantum number value will be plus half. So that is just the analysis. Is that okay? That is the analysis. We are going to move on to our next question. I think this is question number 10. So let's move on to our next question, number 11. Which of the following has 7 degenerate orbitals? I've already answered that. You see, question number 10, I didn't click anything because the correct answer is not there. All right. Then question number 11, which of the following has degenerate orbitals? We just explained that. That is f-orbital. The correct option is D. Question 12, dash determines the direction of angular momentum of electrons and describe the orientation of orbitals in space. The correct answer is magnetic quantum number. Okay, magnetic quantum number. It is that quantum number that gives us information about the direction of angular momentum of the electrons. It also gives us information describing the orientation, how the orbitals are arranged in space. I don't know, let me just mention this quickly. I don't know if you've observed maybe this issue of p orbital having 3 degenerate orbitals. Sometimes when it is being drawn, there is this thing they draw with lobes. You will see one lobe facing up and then 2 others facing down, something like that. You can find that up, right, in your textbooks and stuff like that. Okay, so just take note of that. That's the information that magnetic quantum number gives to us, the direction of angular momentum and the orientation of the orbitals. But before I move on to question number 13, let me say this, okay? The angular momentum of electrons is given by azimuthal quantum number. That is why the azimuthal quantum number is also called the orbital angular momentum quantum number. But in that case, it gives us information about the shell that an electron belongs to. Now, what if we want to know the direction of that angular momentum? That is where the magnetic quantum number now comes in. The magnetic quantum number helps you to get the direction of the orbital angular momentum quantum number. All right, we are moving on to question number 13. And the question we have there, the value of L depends on, and the correct answer is option A. The value of L depends on N. Yeah, the azimuthal quantum number L, to get the value, it depends on principal quantum number N. And I've actually told you the formula. L is equal to N minus 1. So L depends on N. This takes us to question number 14. We are approaching the end because we actually have 15 questions from this topic that we consider. One of the following refers to the subshell that an electron belongs to? The correct answer is subsidiary quantum number. You see, so an examiner can use different names. I think this particular question 14 is actually the same with question 1, if I'm not mistaken. Okay, this is our exam focus quiz on maths, complex numbers. Okay, we are still going to review that, but not today anymore, not in this video. All right, question number 1. Which of the quantum numbers determine the energy sublevel in an orbital? The correct answer is azimuthal. This question number 1 is the same as question number 14. Yeah, take note. Instead of using azimuthal quantum number, now we are calling it subsidiary quantum number. So please, dear friends, you want to take note of these, okay? Subsidiary quantum number, azimuthal quantum number, orbital angular momentum quantum number, they are the same. So the correct answer is option A for number 14. And then this takes us to our last question. Somebody did something wonderful in that question number 10, and I really appreciate that. Okay, the student had to go further to analyze that. And of course, the student has won himself a prize. Okay, together with other students that have actually done well. I think question 15, the last. Which of the following quantum numbers arise from the solution of the radial part of the amplitude of Schrodinger's energy equation? None of the entry is actually correct. The correct answer here is B, the radial quantum number. You know, in the Schrodinger's equation, the solution obtained from the radial part of the amplitude in Schrodinger's equation. The take note, radial quantum number is the same as principal quantum number. All right, so that is that. On the GMAETS 41's video lessons and lesson notes, you have all these things explained. So to learn more, contact GMAETS 41 to register for tutorials. You know, you can also decide to become a channel member on YouTube here, and you follow up with our classes. So this is much we are taking, and I hope you've learned something wonderful. So after this quiz, for those that took it, yeah, I have a giveaway prize to 3 students. Yeah, 3 students that actually attempted the quiz and they did very well. At least none of them scored less than 95%, you know, of the quiz. So they're going to get ready. You know, they would be given the prize allotted for this. So we have Henry, we have Ehije, and we have Marianne. So these 3 students, they did wonderfully well. Okay, so I'm going to be giving you airtime. Yeah, that is what I do for now to encourage you. Okay, so I'm going to give you airtime for Henry because of this wonderful analysis he did here. Okay, going to be giving you the highest share of the airtime. Okay, and then the other 2, you're going to go with the same unit of airtime for your good attempt as well too. Like I said, all the attempts was wonderful, right? Not less than 95% of accuracy in your answers. All right, guys, I hope we've done justice to this and I hope you learned something wonderful. So you can share this link to your friends, okay? Share this video and then invite them to subscribe to this channel, okay? Let them become channel members. For any who wish to join our physical tutorials, please, I invite you to contact GMAETS 41 and join our physical tutorial on campus in Unizig, okay? And there are so much more to learn. GMAETS 41 committed to giving you the best and preparing you for your A splashes. First class, the only academic language that I understand. All right, so I'll be seeing you in my next video. Don't forget your workbooks, Math 101, Phys 101, and Chem 101. They are available on this platform, and if you wish to get access to it, go on ahead for all of them. Okay, you can select and join GMAETS 41 on the diamond level. If you want to get access to all 3 of the workbooks, okay, join GMAETS 41 on the diamond level, and of course you get access to them. All right, take care of yourself and have a lovely day.